Thank you for the very nice introduction. Hi, everyone. My name is Xinglin. I'm from Iowa State University. I'm right now a PhD student working on bioinformatics, computational biology. So today, it's a pleasure to share one of my project with you. It's a method of enrichment analysis we developed, and we call it CLEAR. Starting from the introduction, so the first enrichment analysis framework was introduced in 1999, and over the past 2 decades, there are hundreds of methods and tools were developed. And different names of this kind of method was called for different use cases, such as the function enrichment, pathway analysis, enrichment analysis, etc. But the fundamental goal remains the same, disregard like what they are called. They try to identify the over-representative sets, like function or pathway, regarding the attributes of the elements within those sets. The elements can be like gene, metabolites, SNPs, etc. Here's a kind of example for a general use case of how people use enrichment analysis in their pipeline. For example, a case control transcriptomic study, you always get you already get a gene expression matrix from RNA-seq or a microarray, and with that information, you can do some like differential expression analysis. And then after that, you get a ranked gene list based on the statistic you got from that test. And with that information and also some annotation reference like gene ontology database, you can do enrichment analysis. And in the end, you'll get some enriched functions. And the method here, the enrichment analysis, try to find the gene sets that include as many notable genes as possible and as few non-notable genes as possible. And what I mean notable is, like, for example, on the ranked gene list, you want to capture the very meaningful genes there. There are some existing enrichment analysis method, like the ORA, which is typically the traditional statistical test. For example, the Fisher-Exact test, and also functional category scoring is another type of enrichment analysis, like the very famous GSEA belongs to this category. But this kind of traditional method, they have the same issue, which it tests the gene set individually. So that brings the multiple testing issue, and in the result, probably you already noticed, like maybe you have experience that there are a lot of false positives, and they have to do some multiple testing corrections. And also, because it tests the gene set individually, they often yield very redundant result when you use the data set like gene ontology, which has a parent-child structure. That brings some difficulty to interpretation as well. And there's another type of enrichment analysis method. It's called set-based method, like GenCompBio and MGSA are the member of this category. This kind of method model all gene sets collectively. That way, they avoid the multiple testing issue and also redundancy issues. Here, I want to introduce a little bit more on MGSA because that's a method that our method is based on. So this one is a Bayesian network model with binary nodes. So each node has 2 states, like on or off. It has 3 layers. First, the hidden layer of the terms annotated as T here, which represent the true state of gene set, being on or off, or enriched or not enriched. And the second layer is the hidden layer of the gene, which are the true state of the genes. And the O layer is the observed layer of the genes, which you get that from your experiment. Here with other parameter like Q and alpha and beta, Q basically is on the very left, is the probability of the term being activated, and alpha and beta are the true false positive and false negative rates, like connecting the hidden layer and observed layer. And with all those information and structure of the network like this, we have the joint conditional probability like this. And MGSA will try to maximize its probability to infer the true state of the hidden layer of the terms, given the information we have in the observed layer using Markov chain Monte Carlo algorithm. However, it also has some limitations because all nodes are binary, so it also requires binary input. Like in the observed layer, it classifies the genes to perturbed group and unperturbed groups that require some arbitrary thresholding. Like for example, if you're using p-values, and maybe you want to use a 0.05 to set a cutoff there, and whatever is smaller than 0.05, then the gene is marked as kind of perturbed and feed into the algorithm. And just because of that, it does not utilize the full gene level information. It's provided from the upstream analysis, for example, the DE analysis. So here comes our motivation. The traditional method, ORA and FCS, they are individual testing method. They have their own shortcoming for like redundancy problem and also multiple testing problem. The ORA also usually they use a binary input. The FCS, like GICA, they take the continuous input, but they only use that information for ranking and weighting, and then followed by a non-parametric test, which is known to have like low statistical power. The set-based method, like MGSA, they use the Bayesian framework, which get rid of the redundancy and multiple testing issue, but also just use the binary input. So our goal is just to take the good things. We want to take advantage of the Bayesian framework and directly model the continuous statistic to improve the power and performance of the model. So here comes our method, CLEAR. So on the left is MGSA, on the right is CLEAR. And the main difference between the H and O, which unfortunately I do not label here. So main difference, let me see if I can, laser pointer. So main difference is here, the connection between the H layer and the O layer. So MGSA uses a kind of Bernoulli probability, alpha and beta, which typically says, for the genes that are truly activated, it has a probability of 1 minus beta, which is true positive rate to be observed as perturbed, and has a probability of beta, which is false negative rate to be observed as unperturbed. And for the genes that are not activated, similar thing, like alpha is false positive, and 1 minus alpha is true negative, right? But for CLEAR, we have different assumption on this. We say Bernoulli is too simple. Instead, we have a kind of assumption, say, for the genes that are truly activated, their test statistic or whatever statistic you choose has a very distinct distribution than the genes are not activated. So basically, we want to model the two statistics with two different distributions. For example, if we want to model the p-values, we know when sample size and effect size are efficiently large, negative log p follow approximately normal distribution under the alternative and follow exponential distribution under the norm. So here, our observed statistic will be a negative log p, and FA will be a truncated normal distribution. We use a truncated distribution here. It's because no matter how you draw a normal distribution, they're always a part that fall on negative interval, but the negative log p is always positive. So we get rid of negative part and scale the positive part accordingly. And also the other distribution for the null, we use exponential, which is by definition of p-values. And with that selection of distribution, we can write down our likelihood like that. And then we use some Matrova testing MCMC to sample from the posterior distribution once we maximize that likelihood, and then rank our gene set based on their posterior probabilities. Right, so that's our method. And we test our method and also other popular method, ORA, GSEA, on three metrics: redundancy, phenotype relevance, and also precision recall. For the redundancy, we use 15 RNA-seq datasets from TCGA. We run our method and also other methods on those methods, on those datasets, and assess the top 20 gene sets for their overlaps. And here we can see in general, the set-based method performed very well on this redundancy metric compared to the traditional methods. And CLEAR performed especially well, even better than MGSA on redundancy performance. And also we know the redundancy has a positive correlation with the gene set size. So typically if your gene set is very large, then there are very more chance for it to overlap with other gene sets. But in here, we see the redundancy is not biased toward that metric because CLEAR return like generally fairly large gene set, but the redundancy is very small. And we also validate our method on some real data. So the same data from TCGA, we use 15 different cancer types. We use a metric called phenotype relevance, which is developed by another research group that they have a collection of experimentally validated reference gene set. And we just compare our result with their reference and see if there's a good match. So CLEAR does better than MGSA on this metric, but they are not as good as the traditional ones. This is because this metric, like field time relevance, is a little biased to the individual testing method, because when they build that kind of reference gene sets, they do not consider redundancy. So in their collection, they have some parent, child, and also some genes that are very highly overlapped. So because we're using a similarity metric, like a weighted correlation, so in the naturally, the set-based method that does not have redundancy in the result perform poorly. For this, we're trying to work on a fix on this metric, and also looking for other like gold standard like data set to validate our method on. And lastly, we test our method on some in silico data, because in silico data can actually define what is the ground truth. So we use precision recall to evaluate how effectively each method identifies the true gene sets given different noise level. And I generate in silico data with p-values and also controlling different noise levels by controlling the quantity and quantity of signals. And in general, like CLEAR does very well on this metric, except for the last one. So when the signal quantity and quantity is not very obvious, CLEAR does slightly worse than MGSA. But once the signal quantity and quantity goes up, CLEAR is able to capture that information and very well. And CLEAR is also like does way better than the traditional method, GSEA and ORA on this metric. And that will be a last slide for the results. And I want to thank for my colleagues and Dr. Dorman and Dr. Kadelka, and also thank to my university for providing the fund for this trip. And also thank you for your attention, and I'm ready to take any questions.
Hi, I was wondering, like, how is it possible to like build in uncertainty in the terms themselves? Like, so say you're applying this to a model or something that's like not really a well-studied organism, and so your annotations are actually themselves uncertain. Like, could you extend this kind of framework to handle that type of uncertainty in the ground truth?
Yeah, definitely. So the beauty of the Bayesian network is, like, you have a structure like this, and once you have some other information that, like, you have some prior knowledge for your organism, you can incorporate that maybe for another layer of information here into that inference, and that will capture that. And that's basically that.
Cool.
Yeah,
thanks.
Thank you.
Yeah.
This is another question from online. Is CLEAR available for public use?
I'm sorry?
Is CLEAR available for public use?
Not yet, because we're showing example for modeling the p-value. I'm working on modeling the other statistics as well. And once we finish that, we'll like make at least a preprint, and then stay tuned to maybe archive. And when we publish it on the archive, at least we'll have the GitHub like a repo available to use. Yes.